consider a point P in a plane. If you are to mark another point A, 10 centimeters away from point P, what will be its possible location? Point A can lie at any position on a circle with its center at P and radius equal to 10 centimeters. In this case, the shift in position from point P to point A has a fixed magnitude, which is equal to a distance of 10 centimeters. But it has no fixed direction. We say that distance PA is 10 centimeters. Now, suppose you have to mark point A such that its distance is 10 centimeters from P in the east direction. What will be the possible location of point A? Here, the shift in position from point P to point A has a fixed magnitude equal to a distance of 10 centimeters as well as a fixed direction. In this case, we say that displacement PA is 10 centimeters in the east direction. Quantities like length, mass and time, which are characterized only by their magnitude, are called scalar quantities. Quantities like displacement, force, and electric and magnetic fields, which are characterized by both their magnitude as well as direction, are called vector quantities. Let us take another example of a line L in a three-dimensional space. A straight line extends towards both the sides endlessly in space to an infinite length. If we indicate the direction of line L with an arrow in any one of these two directions, it becomes a directed line. Now consider 2 points A and B on line L. Line segment AB has a fixed magnitude and a direction that is the same as the direction of line L. Thus, AB is a directed line segment. Directed line segment AB is written as shown and read as vector AB. Directed line segment AB can also be represented by a small case letter A with an arrow over it and read as vector A. Point A, which is the starting point of vector AB as per the given direction, is called the initial point of vector AB. Point B, which is the end point of vector AB as per the given direction, is called the terminal point of vector AB. The arrow placed above vector AB always points from the initial point to the terminal point of the vector. The magnitude of vector AB is represented as shown. The magnitude of vector AB is equal to the length of line segment AB. If the direction of the directed line is reversed, we get vector BA. In this case, the initial point is B and the terminal point is A, and vector BA is equal to minus vector A. Note that the magnitude of vectors AB and BA is the same and equal to the length of line segment AB. Now consider a point P in a three-dimensional coordinate system. Vector OP, with its initial point at the origin and its terminal point at P, is called the position vector of point P with respect to the origin. The position vector of point P with respect to the origin can also be represented as vector R. As shown, you know the distance formula to find the distance between two given points in a three-dimensional space. Using the distance formula, we get the magnitude of the position vector of point P with respect to the origin. It is equal to under root of x square plus y square plus z square. The small letter r, written without the arrow, represents the magnitude of vector r. Let alpha, beta and gamma be the angles made by vector r with the positive directions of the x, y and z axes respectively. Then the angles alpha, beta and gamma are called the direction angles of vector r. The cosines of the direction angles of a vector are called its direction cosines. Thus, cos alpha, cos beta and cos gamma are the direction cosines of vector r. By convention, the direction cosine cos alpha is denoted by L, cos beta is denoted by M, and cos gamma is denoted by N. Now, let us find the values of the direction cosines of vector r. Let PA be the perpendicular drawn from point P to the x-axis. Thus, length OA is equal to the x-coordinate of point P. Let PB be the perpendicular drawn from point P to the y-axis. Thus, length OB is equal to the y-coordinate of point P. Similarly, let PC be the perpendicular drawn from point P to the z-axis such that length OC is equal to the z-coordinate of point P. Thus, points O and P lie at the opposite vertices of a cuboid with dimensions x, y and z. In right-angled triangle OAP, cos alpha or direction cosine L is equal to OA upon OP or x upon r, where r is the magnitude of positional vector OP. This implies that the x-coordinate of point P is equal to the product of direction cosine L and r, which is the magnitude of positional vector OP. In right-angled triangle OBP, cos beta or directional cosine M is equal to OB upon OP or y upon r, where r is the magnitude of positional vector OP. This implies that the y-coordinate of point P is equal to the product of direction cosine M and r, which is the magnitude of positional vector OP. Similarly, in right-angled triangle OCP, cos gamma or direction cosine N is equal to OC upon OP or Z upon R. Again, this implies that the Z-coordinate of point P is equal to the product of direction cosine N and R, which is the magnitude of positional vector OP. The quantities LR, MR and NR, which represent the coordinates of the terminal point of vector R in terms of its direction cosines and magnitude, are called the direction ratios of vector R. By convention, the direction ratios of a vector are denoted by the letters A, B and C as shown. Now, let us derive an interesting relationship between the sum of the squares of the direction cosines of vector R. Substituting the values of the direction cosines cos alpha, cos beta and cos gamma from the previous expression and simplifying, we get that the sum of the squares of the direction cosines of vector R is 1. This relationship is true for all vectors. Now, let us see if a similar relationship exists between the direction ratios of vector r. On simplifying the previous equation, we get that the sum of the squares of the direction ratios of a vector is equal to the square of its magnitude. This also implies that the sum of the squares of the direction ratios of a vector is not equal to 1 unless the magnitude of the vector is equal to 1. You already know that a vector is a directed line segment. You also know that the starting point of a vector is called its initial point, and its end point is called its terminal point. A vector whose initial and terminal points are the same is called a zero vector. A zero vector is denoted by 0 with an arrow above it. Since the length of the line segment forming a zero vector is nil, the magnitude of a zero vector is 0. A zero vector has no fixed direction. A vector whose magnitude is 1 is called a unit vector. A unit vector is represented as shown. Two or more vectors having the same initial point are called co-initial vectors. Here vectors AB and AC have the same initial point A, and thus are co-initial vectors. Now consider a line L parallel to vector AB. Also consider vectors EF, MN and OP, all parallel to line L, like vector AB. Two or more vectors that are parallel to the same line are called collinear vectors. Here vectors AB, OP, MN and EF are parallel to the same line L. Hence, they are collinear vectors. Since vector AC is not parallel to line L, it is not collinear to the other vectors shown here. Observe that collinear vectors may have different magnitudes. Also note that collinear vectors may have opposite directions. Now, consider vectors OP and AB with the same direction and magnitude. Two vectors with the same direction and magnitude are called equal vectors. Hence, vectors AB and OP with the same direction and magnitude are equal vectors. Note that equal vectors may have different initial and terminal points. Now, suppose we reverse the direction of vector OP. So now we have two vectors AB and PO with equal magnitude, but opposite directions. Two vectors with the same magnitude but opposite directions are called negative vectors of each other. Thus, vector PO is called the negative vector of vector AB and is also written as vector BA. Similarly, vector AB is called the negative vector of vector PO and is also written as vector OP. Note that all equal vectors are collinear vectors, but all collinear vectors are not equal. A pair of collinear vectors may be negative vectors of each other. Consider a vector AB as shown. Let us change the position of vector AB such that its direction and magnitude do not change. Then, in each new position, vector AB is parallel to its initial position and represents the same vector. A vector that is independent of its position is called a free vector. Thus, a free vector is not bound by any fixed initial or terminal points. In this chapter, we will deal only with free vectors. Now consider two free vectors, A and B. To add the given vectors A and B, we shift one of the vectors without changing its magnitude and direction, such that its initial point coincides with the terminal point of the other vector. Let vectors A and B be represented by the vectors AB and BC respectively. By joining A and C, we get triangle ABC. Now, by the triangle law of vector addition, vector AC represents the sum of vector AB and vector BC. Observe that the terminal point of vector AB and initial point of vector BC are the same. Upon adding vectors AB and BC, the resultant vector is AC, whose initial point is A and terminal point is C. Let us reverse the direction of vector AC to get vector CA. The net displacement in moving from points A to B, B to C, and C to A is represented by vector AA, whose initial and terminal points both lie at point A. Thus, the sum of the vectors representing the three sides of a triangle in order is a zero vector. Now, let us draw a vector BC' that is equal in magnitude but opposite in direction to vector BC. Thus, vector BC' is equal to minus of vector BC. In triangle ABC', vector AC' is equal to the sum of the vectors AB and BC'. We know that vector BC' is equal to negative of vector BC. Substituting the values of vectors AB and BC, we find that vector AC' is equal to vector A minus vector B. Consider a man at point O on the left bank of a river. The man starts swimming towards point A on the right bank of the river in a direction perpendicular to the flow of the river, with the velocity represented by vector A. The man is also acted upon by the velocity of the water flowing in the river. Under the influence of the two velocities, the man actually moves at an angle to line OA and reaches the right bank at point C. Let vector AC be equal to vector B. The velocity with which the man swims from point O to point C is the sum of velocity vectors A and B. Complete the parallelogram OACB. Since OACB is a parallelogram, vector OB is equal to vector AC. Therefore, vector OB is equal to vector B. We observe that the sum of vectors OA and OB is represented by the diagonal of the parallelogram passing through the common point of vectors OA and OB, that is, point O. The parallelogram law of vector addition states that the sum of two vectors representing adjacent sides of a parallelogram is given by the diagonal of the parallelogram passing through the common point of the two adjacent sides. Thus, by the parallelogram law of vector addition, vector OA plus vector OB is equal to vector OC. The opposite sides of a parallelogram are equal and parallel. Thus, vector AC is equal to vector OB. Using the triangle law of vector addition from triangle OAC, we get vector OA plus vector AC is equal to vector OC. Thus, we see that the triangle and parallelogram laws of vector addition are equivalent to each other. Now, let us prove that vector addition is commutative. Let us consider two vectors, A and B. Consider two adjacent sides, AB and BC, of a parallelogram ABCD, representing vectors A and B respectively. By the triangle law of vector addition, vector AB plus vector BC is equal to vector AC, which is vector A plus vector B. Since the opposite sides of a parallelogram are equal and parallel, vector AD is equal to vector BC, and vector DC is equal to vector AB. Applying the triangle law of vector addition to triangle ADC, vector AC is equal to vector AD plus vector DC, which is equal to vector B plus vector A. Thus, we find that vector A plus vector B is equal to vector B plus vector A. Hence, vector addition is commutative. If we add a zero vector to any vector, the vector remains unchanged. Hence, a zero vector is called the additive identity of vector addition. Now, let us prove that vector addition is associative. Consider three vectors, AB, BC, and CD, representing vectors A, B, and C respectively. By the triangle law of vector addition, the sum of vectors AB and BC is equal to vector AC, which is equal to vector A plus vector B. Now, consider triangle ACD. The sum of vectors AC and CD is equal to vector AD, or the sum of vectors A and B plus vector C. Now, let us add the vectors in a different way. Consider triangle BCD. By the triangle law of vector addition, the sum of vectors BC and CD is equal to vector BD, which is vector B plus vector C. Now, consider triangle ABD. The sum of vectors AB and BD is equal to vector AD, or the sum of vectors B and C. Equating the value of vector AD from equations 1 and 2, it is proved that vector addition is associative. Consider a vector R. If we multiply vector R by 2, we get another vector, 2R, with the same direction as vector R, but twice its magnitude. Similarly, if we multiply vector R by -3, we get another vector, -3R, opposite in direction to vector R and with thrice its magnitude. Note that in these cases, we have multiplied vector R with the scalar quantities 2 and -3 to get new vectors. If we multiply any vector, say vector R by a scalar quantity, say lambda, we get another vector lambda R. The magnitude of vector lambda R is equal to the magnitude of the scalar quantity lambda multiplied by the magnitude of vector R. The direction of vector lambda R depends on the sign of the scalar quantity lambda. The vector obtained by multiplying a given vector with a scalar quantity is collinear to the given vector. Now, let us take some special cases. Multiplying a given vector r by -1, we get vector minus r, which is equal in magnitude but opposite in direction to vector r. Vectors r and -r are called additive inverses of each other, and their sum is a zero vector. Multiplying a non-zero vector r with the reciprocal of its magnitude, we get a vector whose magnitude is 1. In this case, the new vector is a unit vector r with the same direction as the given vector and magnitude equal to 1. A unit vector r is denoted as shown. The multiplication of vectors by scalar quantities follow the distributive laws shown here. Consider a three-dimensional coordinate system. Let P be a point in space with coordinates x, y, z. Let us draw a perpendicular PA from point P onto the XOY plane. Let Q and S be the feet of the perpendiculars drawn from point A to the X and Y axis respectively. Complete the parallelepiped as shown. Now, Q, S and R are the points on the X, Y and Z axis respectively, such that OQ is equal to X, OS is equal to Y, and OR is equal to Z. Now, vectors I, J and K are unit vectors along the X, Y and Z axis respectively. Thus, vector OQ is equal to X into unit vector I along the X-axis. Similarly, vector OS is equal to Y into unit vector J along the Y-axis, and vector OR is equal to Z into unit vector K along the Z-axis. From the figure, we have vector QA is equal to vector OS, that is, Y into unit vector J. In triangle OQA, vector OA is equal to vector OQ plus vector QA. Thus, vector OA is equal to X into vector I plus Y into vector J. Again from the figure, we have vector AP is equal to vector OR, that is, Z into unit vector K. In triangle OAP, vector OP is equal to vector OA plus vector AP. Thus, vector OP is equal to X into vector I plus Y into vector J plus Z into vector K. This form of vector OP is called the component form of vector OP. X, Y and Z in their component form are called the scalar components or rectangular components of vector OP. The scalar components of a vector are called its direction ratios. Xi, Yj and Zk in their component form are called the vector components of vector OP. Now, let us find the magnitude of vector OP. In right-angled triangle OQA, the square of the length of the hypotenuse OA is equal to the sum of the squares of the lengths of sides OQ, QA. That is, modulus OA square is equal to x square plus y square. In right-angled triangle OAP, the square of the length of the hypotenuse OP is equal to the sum of the squares of the length of sides OA and AP. Substituting the corresponding values, we get the magnitude of vector OP is equal to the square root of the sum of the squares of its scalar components x, y, and z. Suppose vector OP makes angles alpha, beta, and gamma with the x, y, and z axes respectively. Then the direction cosines of vector OP are given by cos alpha, cos beta, and cos gamma. They are denoted by L, M, and N respectively. If the direction cosines of a given vector are known, then the unit vector in the direction of the given vector can be written as shown. Now, consider a vector A in its component form. Multiplying the given vector A by a scalar, lambda, we get another vector as shown. Now let us learn about some interesting relationships between two vectors, A and B, given in their component forms. To find the sum of two vectors, add the corresponding scalar components, as shown here. To find the difference between two vectors, subtract the corresponding scalar components, as shown here. Vectors A and B are equal if and only if their corresponding scalar components are equal. The given vectors A and B are collinear if and only if there exists a scalar, lambda, such that the component form of one vector is equal to lambda times the component form of the other vector. On simplifying, we find that the two vectors A and B are collinear if their corresponding scalar components are in a constant ratio. Consider 2 points P1 and P2 in space as shown here. Let us find vector P1, P2 by joining the two given points. Let us draw vectors OP1 and OP2 from the origin to the given points, P1 and P2 respectively. Applying the triangle law of vector addition in triangle OP1, P2, we have vector OP2 is equal to vector OP1 plus vector P1, P2. On rearranging the terms in the equation, we get vector P1, P2 is equal to vector OP2 minus vector OP1. Let this be equation 1. If vectors I, j, and k are unit vectors along the x, y, and z axes, respectively, then vector OP1 in component form is given by x1 into vector I plus y1 into vector j plus z1 into vector k. Similarly, vector OP2 in component form is given by x2 into vector I plus y2 into vector j plus z2 into vector k. Let us substitute the component forms of vectors OP1 and OP2 in equation 1. On simplifying, we get vector P1, P2 as shown here. The magnitude of vector P1, P2 is given by the under root of the sum of the squares of its scalar components x2 minus x1, y2 minus y1, and z2 minus z1. Consider a point A, having position vector OA with respect to origin O. Consider another point B, having position vector OB with respect to origin O. AB is the line segment joining points A and B. Let R be a point that divides line segment AB. Point R can either lie between A and B and divide line segment AB internally, or can lie on extended line segment AB to divide AB externally. Let us find the position vector for R in both these cases. First, let us consider the case where point R divides line segment AB internally. Let vectors AB and R represent position vectors OA, OB, and OR for points AB and R, respectively. Let point R divide line segment AB in the ratio m:n. From triangle OAR, we get vector AR is equal to vector OR minus vector OA, which is equal to vector R minus vector A. Similarly, from triangle ORB, we get vector RB is equal to vector OB minus vector OR, which is equal to vector B minus vector R. Since the ratio AR is to RB is equal to m:n, we can say that m into vector RB is equal to n into vector AR. Let us substitute the values of vectors RB and AR in the equation. On simplification, we get vector R is equal to m into vector B plus n into vector A divided by m plus n. This expression gives the position vector of point R that divides line segment AB internally in the ratio m:n. Let us see what happens when point R bisects line segment AB. That is, point R lies at the midpoint of line segment AB. Here the ratio m:n is equal to 1:1. That is, m is equal to n. Putting m is equal to n in the formula for the position vector of R, we get vector OR is equal to the sum of vectors A and B divided by 2. Now, let us consider the case where point R divides line segment AB externally. Let vectors A, B, and R represent position vectors OA, OB, and OR for points A, B, and R, respectively. Let point R divide line segment AB externally such that the ratio AR is to BR is equal to m:n. From triangle OAR, we get vector AR is equal to vector OR minus vector OA, which is equal to vector R minus vector A. Similarly, from triangle OBR, we get vector BR is equal to vector OR minus vector OB, which is equal to vector R minus vector B. Since the ratio AR is to BR is equal to M is to N, we can say that M into vector BR is equal to N into vector AR. Let us substitute the values of vectors BR and AR in the equation. On simplification, we get vector R is equal to M into vector B minus N into vector A divided by M minus N. This expression gives the position vector of point R that divides line segment AB externally in the ratio M is to N. Here are two men trying to move a boulder. Both of them are applying a force along the line of the ropes that they are pulling. The forces exerted by the two men on the boulder can be equated with two vectors A and B inclined to each other at an angle theta. Vector multiplication is of two types. One is dot or scalar product and the other is cross or vector product. The name itself indicates the result. If we use scalar product, the result is a scalar, that is, a real number. If we use vector product, the result is a vector. You will now learn to find the scalar or dot product of two vectors. Let vector A and vector B be two non-zero vectors. The scalar or dot product of vectors A and B is denoted as shown and is defined as the product of the magnitudes of vectors A and B and the cosine of angle theta between them. The range of theta is from 0 degrees to 180 degrees. If either vector A or vector B is a zero vector, then angle theta between them is not defined, and hence their dot product is 0. We know that the magnitude of any vector is a real number and that the cosine of angle theta is also a real number. Therefore, the product of the magnitudes of vector A and vector B and the cosine of the angle between them is a real number. Hence, we can say that the dot product of any two vectors is a real number. Suppose vector A and vector B are non-zero perpendicular vectors. Therefore, the cosine of the angle between them is 0. Hence, their dot product is 0. The converse is also true. Suppose vector A and vector B are non-zero vectors such that their dot product is 0. Then, the two vectors are perpendicular to each other. When vectors A and B act along the same line in the same direction, the angle theta between them is 0. In this case, the dot product of vectors A and B is equal to the product of their magnitudes. If the magnitude of vector A and the magnitude of vector B are equal, then their dot product is equal to the square of the magnitude of vector A. When vectors A and B act along the same line in opposite directions, the angle theta between them is 180 degrees. In this case, the dot product of vectors A and B is equal to minus times the product of their magnitudes. This implies that the dot product of a vector with its negative vector is equal to the square of its magnitude with a minus sign. If the magnitude of vector A and the magnitude of vector B are equal, then their dot product is equal to minus times the square of the magnitude of vector A. If the magnitudes of two non-zero vectors and their scalar product is known, you can find the angle theta between them. The dot product of two vectors is commutative. The properties of dot products that we have discussed so far give some very interesting results. You have studied unit vectors I, j and k along the x, y and z axis respectively. The dot product of unit vectors I, j and k with themselves is equal to 1. This is because each of these unit vectors has a magnitude of 1 and angle theta in this case is 0 degrees. The product of any two of the mutually perpendicular unit vectors I, j and k is 0. This is because angle theta in this case is 90 degrees. You already know that the scalar or dot product of two vectors A and B with angle theta between them is equal to the product of the magnitudes of vectors A and B and the cosine of angle theta. Now, let us observe an interesting property of dot product of vectors. Consider three vectors A, B and C. The dot product of vector A with the sum of vector B and vector C is equal to the dot product of vector A and vector B plus dot product of vector A and vector C. This property is called the distributive property of dot product over vector addition. Now, let us learn about the multiplication of the dot product of vectors with a scalar. The dot product of vectors A and B multiplied by a scalar lambda is equal to the dot product of lambda times vector A and vector B. It is also equal to the dot product of vector A and lambda times vector B. The distributive property of dot product helps us find the dot product of two vectors given in their component form. Consider two vectors A and B. To find the dot product of vectors A and B, we multiply their component forms. We know that dot product is distributive. Using the distributive property, we can expand the dot product as shown here. We know that unit vectors I, j and k are mutually perpendicular to each other. We also know that the dot product of two mutually perpendicular vectors is 0, and the dot product of a unit vector with itself is equal to 1. Substitute the corresponding values in the expansion. Thus, we find that the dot product of vectors A and B is equal to A1b1 plus A2b2 plus A3b3 where A1, A2 and A3 are the scalar components of vector A, and B1, B2 and B3 are the scalar components of vector B. Consider a directed line L and vector OA represented as vector A, making an angle theta with line L in the anti-clockwise direction. We will find the projection of vector A on line L. Drop a perpendicular AB from point A to line L. Now, vector OB, represented as vector P, is the projection vector of vector A on line L. In right-angled triangle OBA, cos theta is equal to OB upon OA. Thus, vector OB or vector P is equal to vector A multiplied by cos theta. The magnitude of vector P is called the projection of vector A on line L and is equal to magnitude of vector A multiplied by cos theta. The direction of projection vector P depends on the angle theta that vector A makes with line L. This leads to some interesting observations. If theta is equal to 0, then vector A lies along line L and projection vector P is the same as vector A and has the same direction as line L. When angle theta lies between 0 and 90 degrees, projection vector P points in the same direction as line L. If theta is equal to 90 degrees, vector A is perpendicular to line L and its projection vector P is a 0 vector. When theta lies between 90 degrees and 180 degrees, cos theta is negative, and hence the direction of projection vector P is opposite to the direction of line L. If theta is equal to 180 degrees, then vector A lies along line L. In this case, its projection vector P is equal to negative vector A, and its direction is opposite to that of line L. When angle theta lies between 180 degrees and 270 degrees, the direction of projection vector P is opposite to the direction of line L. If theta is equal to 270 degrees, vector A becomes perpendicular to line L again, and its projection vector P becomes a 0 vector. When angle theta lies between 270 degrees and 360 degrees, the direction of projection vector P is the same as the direction of line L. Projection vector P of vector A is also equal to the dot product of vector A and unit vector P along line L. Let us replace line L with another vector B and find the projection of vector A on vector B. The projection vector of vector A on vector B is equal to the dot product of vector A and unit vector along vector B. The projection vector of vector A along vector B is also given by the dot product of vectors A and B divided by the magnitude of vector B. Let us look at the component form of vector A again. The scalar components A1, A2 and A3 of the given vector A are the projections of vector A on the x, y and z axis respectively. You can also determine the direction cosines of a vector from its component form as shown here. Direction cosines can also be used to express a vector in its component form. A unit vector can be represented using its direction cosines as shown here. You must have observed that when a screw is placed on a wooden board and rotated in an anti-clockwise direction, the screw advances into the board. Now, let us study this behavior of the screw in terms of vectors. Consider the x and y axis as shown. Observe the direction of motion of the screw when it rotates from the x-axis towards the y-axis. As you can observe, when the screw rotates from the x-axis towards the y-axis, it advances along a path that is perpendicular to both the x and y axis. This path can be represented by the z-axis. This example illustrates a right-handed coordinate system. In the right-handed coordinate system, if you curl the fingers of your right hand in the direction of the movement from the positive x-axis to the positive y-axis, your extended thumb will point in the direction of the positive z-axis. The understanding of the right-handed coordinate system is essential to understand the vector or cross product of two vectors. Consider two non-zero vectors, P and Q. Let theta be the angle between vectors P and Q such that the value of theta lies between 0 degrees and 180 degrees. Then, the cross product of vectors P and Q is equal to the product of their magnitudes, the sine of angle theta, and a unit vector n. Here, unit vector n is perpendicular to both vector P and vector Q. Note that unit vector n acts along the vector equal to the cross product of vectors P and Q. Since the cross product of two vectors is also a vector, it is also called a vector product. Thus, vectors P, Q and n form a right-handed coordinate system that moves in the direction of n when it rotates from vector P towards vector Q. Note that if either vector P or vector Q is a zero vector, their cross product is also a zero vector. When the cross product of two vectors is performed, the resultant vector can be written as shown here. Here, modulus P modulus Q sine theta is the magnitude, and n is the unit vector. So the resultant is also a vector. We know that the cross product of vectors P and Q is a vector perpendicular to both of these two vectors. We also know that the unit vector n in the cross product of two vectors P and Q is also perpendicular to the vectors P and Q. Hence, the cross product of two vectors P and Q and the unit vector n are collinear. Consider two non-zero vectors P and Q. If the two vectors are parallel to each other, then the angle theta between them is 0. Since sine 0 is 0, the cross product of two parallel vectors is a zero vector. Thus we can say that the cross product of two non-zero vectors is a zero vector if and only if the two vectors are parallel to each other. This leads to some interesting observations. Since every vector is parallel to itself, the cross product of a vector with itself is a zero vector. Also, the negative of a vector makes an angle of 180 degrees with the given vector. Since sine 180 is also zero, the cross product of a vector with its negative vector is also a zero vector. You already know that unit vectors along the x, y and z axis of a three-dimensional coordinate system are denoted by unit vectors I, j and k, respectively. From the discussion so far, it follows that the cross products of unit vectors I, j or k with themselves is a zero vector. Now consider two vectors p and q that are perpendicular to each other. This means that angle theta between them is 90 degrees. Since sine 90 is 1 and n is a unit vector, the magnitude of the cross product of two mutually perpendicular vectors is equal to the product of their magnitudes. If you know the magnitude of the cross product of two vectors and the product of their modulus, you can find the value of angle theta between them using the formula shown here. You already know that the cross product of vectors p and q, when p rotates towards q by angle theta, is given by the formula shown in equation 1. The vector representing the cross product of vectors p and q is in the direction of unit vector n. Observe what happens when vector q rotates towards vector p by angle theta. In this case, the vector representing the cross product of vectors q and p points in the direction of unit vector n dash. Comparing the two figures, we can see that vectors n and n dash are in opposite directions. Putting vector n dash equal to minus vector n in equation 2, we get equation 3. Comparing equations 1 and 3, we find that the cross product of vectors p and q is equal to the negative of the cross product of vectors q and p. This leads us to the conclusion that the cross product of vectors is not commutative. From the discussion so far, we can again make some interesting observations about unit vectors I, j and k pointing along the x, y and z axis of a three-dimensional coordinate system. From the property of cross product of perpendicular vectors, we get that the cross product of unit vectors I and j is equal to unit vector n that is perpendicular to both vectors I and j. Since unit vector k is also perpendicular to vectors I and j, we can say that the cross product of unit vectors I and j is equal to unit vector k. From the property that states that cross product is not commutative, we get the cross product of vector j and vector I is equal to the negative of vector k. Similarly, we arrive at the results shown here. Now, let us explore another interesting property that states that if two vectors p and q form the adjacent sides of a triangle, then the area of that triangle is equal to half of the modulus of the cross product of vectors p and q. To prove this property, we draw QR perpendicular to OP as shown. By formula, area of triangle OPQ is equal to half of the product of base OP and height QR. From right-angled triangle OQR, we get QR is equal to OQ sine theta, where theta is the angle between vectors P and Q. Let us substitute this value of QR in equation 1. Now, OP is equal to magnitude of vector P and OQ is equal to the magnitude of vector Q. This implies that the area of triangle OPQ is equal to half of the product of the magnitudes of vectors P and Q and sine theta. The product of the magnitudes of vectors P and Q and sine theta is equal to the magnitude of the cross product of vectors P and Q. Thus, the property is proved as shown. We have another property that states that if two vectors P and Q form adjacent sides of a parallelogram, then the area of that parallelogram is equal to the modulus of the cross product of vectors P and Q. To prove this property, we draw QS perpendicular to OP as shown. By formula, area of parallelogram OPRQ is equal to the product of base OP and height QS. From right-angled triangle OQS, we get QS is equal to OQ sine theta, where theta is the angle between sides OP and OQ. Let us substitute this value of QS in equation 1. Now, OP is equal to magnitude of vector P and OQ is equal to magnitude of vector Q. This implies that the area of parallelogram OPRQ is equal to the product of the magnitudes of vectors P and Q and sine theta. We know that the product of the magnitudes of vectors P and Q and sine theta is equal to the magnitude of the cross product of vectors P and Q. Thus the property is proved as shown. Vector product is distributive over addition. Thus, for any three vectors P, Q and R, the cross product of vector P with the sum of vectors Q and R is equal to the sum of the cross products of vectors P and Q and vectors P and R. We also have that the cross product of vectors P and Q multiplied by a scalar lambda is equal to lambda into vector P cross vector Q or vector P cross lambda into vector Q. Now we will find the cross product of two vectors given in component form. Consider two vectors A and B as shown. Let us consider their cross product. We know that cross product is distributive over addition. Using the distributive property, we can expand the cross product as shown. We know that unit vectors I, j and k are mutually perpendicular to each other. We also know that the cross product of a unit vector with itself is equal to 0. We have already observed the cross products of mutually perpendicular unit vectors as shown here. Substituting the corresponding values, we get the equation as shown here. On simplifying, we get the cross product of vectors a and b as shown. The cross product of two vectors a and b can also be expressed as a determinant as shown here.